The objective of this video is to understand how organolithium and organomagnesium compounds are prepared and to understand the basic reactivity of organolithium and organomagnesium compounds. First, we are going to look into the organolithium compounds. How these organolithiums are prepared is basically by using a halide, either alkyl halides or aryl halide. Now you can see this is an aromatic compound. You have benzene and chlorine attached to the benzene ring. So this is like benzyl chloride. So you can see both of them, they have carbon and hydrogen chain, and then you have this X group, which can be things like fluorine, chlorine, bromine, or iodine. So what you basically have is Rx group. To that you add lithium, and you can see it is in the elemental form, and this reaction is carried out in a nonpolar solvent like hexane. Pentane, hexane, these are alkanes. You have only carbon and hydrogen, and they are highly nonpolar. So under nonpolar condition, if you react metallic lithium with an alkyl halide or aryl halide, you can get this organolithium compound, and you have some basic understanding how we have named them. You have the organo part first, the organic component named first, and then the metal. So you can see this is butyl group. You see 4 carbon atoms. So this is butyl lithium. And this one, you can see it is chlorobenzene. You get phenyl lithium. How we prepare organomagnesium is by reacting magnesium. Again, we can have alkyl halide or even double bonded alkyl groups or vinylic compounds. In this preparation of organomagnesium compounds, as solvents we use either diethyl ether or THF. THF is what we call as tetrahydrofuran, which is you have oxygen and this 5-membered ring. So the purpose of diethyl ether and THF is as a solvent. Under this condition, we can generate this organomagnesium compound, which we commonly call as Grignard region. Now this discovery of this Grignard region or the organomagnesium compounds is actually a Nobel Prize winning finding. It has opened a new window to perform many different organic syntheses. The purpose of these solvents in preparation of organolithium compounds, you notice that we are using a solvent like hexane, a nonpolar solvent, but in this one we are particularly using something like THF and diethyl ether. If you check the structure of diethyl ether, you have oxygen, diethyl, you have 2 ethyl groups. Then you have the lone pair. Now you can see in the prepared organomagnesium compound, what happens is that magnesium is inserted between the carbon and bromine. So it is more like an insertion of magnesium between the carbon and this X group. So in both occasions you can see magnesium being inserted. Now once magnesium is inserted, just think how many electrons magnesium is already holding. So if I consider this whole group as an R group, this is the organomagnesium compound is more like RMX. Now this X is things like bromine and chlorine, and this R is the carbon chain. Now think about the Lewis structures. Each straight line, each bond represent 2 electrons. Now at this point, magnesium is actually sharing 4 electrons. It has an incomplete octet. How about these solvents? Now these solvents have these lone pairs. So what these solvents basically do is stabilize this Grignard region and keep it under dissolved form by coordinating with magnesium by using these lone pairs. So that means these solvent molecules will share its electrons like this. Now in that way, magnesium will be able to complete an octet. It's having 1, 2, 3, 4, 5, 6, 7, 8 electron, and the purpose of these solvents is to keep this magnesium in dissolved form by coordinating with magnesium and assisting it to complete the octet. Otherwise, there will be magnesium shavings in the solution and it might settle down as solid form. We don't want things in the solid form, we want it as a reagent in the dissolved form. That is the whole purpose of this solvent being used. Alright, now think about general chemistry. What you have here is a carbon and then a metal, either a group 1 or group 2 metal. Lithium is group 1, magnesium is group 2. Now metals, what kind of electronegativity they have with respect to carbon? Metals have a low electronegativity. So that means they tend to get a positive charge. If they are getting a positive charge, that means we are basically creating a negative charge on the carbon. So that way carbon can work as an ion. So basically we are generating a negative charge on this carbon by creating this organolithium or organomagnesium compounds. Now this form of this organometallic compound can act as a base or as a nucleophile. Now you can see there is high electron density, so it can function as a nucleophile. That means it can react, it can be attracted to a positive end. So that means if you can create a carbocation, this nucleophile will go and attack the carbocation, and because it is going to act as a base, actually these are very strong bases. They are so strong that they can actually even react with very weak acids like water. For example, if you have an alkyl halide, let's see, something like this. You have the carbon chain and you have Br. Now this is your Rx, and you can prepare the Grignard reagent by adding magnesium and THF. You're going to prepare your Grignard reagent. That is your Grignard reagent. Now just assume if you have water in your solution, this Grignard reagent will very rapidly react with water and it will produce the alkane. So it will make MgHbr. It's going to make the alkane plus, where is that? Plus it is making MgHbr. So this is not the reaction we prefer, so it is very important that we conduct these reactions under anhydrous conditions. If you have any moisture in your reaction medium, you will end up with an alkane instead of the desired product. Now most often the product from these organometallic organometallic compounds, organolithium or organomagnesium compounds, they are going to be alcohols. We are going to see some of the reactions these organometallic compounds can show. For example, if we take this aldehyde. If you start with this aldehyde and first add an organometallic compound, either organolithium or organomagnesium, can have our CH2, let's say the lithium compound. So the first step is you add the organolithium compound. As a second step, we add an acid to follow the rest of the step. So this is like two-step process. In the first step, what we have is the addition of this organometallic compound that we have prepared. What basically happen in these processes is that, oxygen, it is very electronegative atom, so it attracts electrons from this double bond toward itself. So that means oxygen is going to have a slightly negative charge. That means the carbon over here is going to hold a positive end. And the organolithium, organomagnesium compounds, lithium is going to have the plus charge and carbon have the negative charge. So that means this carbon can go and attack this positive carbon. Meaning now you have a negative charge on oxygen, you have hydrogen, and you have this CH2 R group attaching. Now this negative end can interact with the acid in the medium, so at the end it will result in an alcohol. So what kind of alcohol is this? Is it primary, secondary, or tertiary? Now this one is a secondary alcohol. Let's check a ketone. Now this is a ketone, a similar kind of reaction. First you add the organometallic compound, and then you add acid as a second step. Same kind of mechanism. The carbonyl group, the oxygen attract electrons like this. It creates a partial negative end on oxygen and a positive end on the carbon here. Now here you know how the charge separation is like. Now this negative carbon, remember the arrows always shown as going from high electron density to low electron density. It's never the reverse way. It's always going from negative ends to the positive ends. That will result in formation of this intermediate state. This negative end is going to get attracted to that, resulting in Now what kind of alcohol is this? This is a tertiary alcohol. So aldehydes lead to secondary alcohols and ketones leads to tertiary alcohols. You can do the similar kind of mechanism with Grignard reagent, which is the organomagnesium compound. If I do a similar reaction with organomagnesium, again I'm having aldehyde. Similar to the above reaction, the first step is adding the organomagnesium compound, and as a second step you can add the acid. Similar kind of mechanism, again the electron withdrawal nature is same. Magnesium, it has a positive charge, and carbon is going to have a negative charge, so this carbon is going to get attracted. Right. So what kind of alcohol you have? It is again secondary alcohol. Again, this is an aldehyde. So if you are using an aldehyde, doesn't matter whether it is the lithium compound or the magnesium compound, you will end up with secondary alcohol with aldehydes. And if you do the same mechanism for ketone with the magnesium compound, you're again going to end up with tertiary alcohol. Now these organolithium or organomagnesium compounds are going to have some limitations. Now earlier I mentioned that they are strong bases and also they are very good nucleophile. And sometimes their the base activity can be much more stronger than nucleophilic activity. Now here in these reactions you can see the whole purpose of having this metal attached to a carbon is to generate this partial negative charge on a carbon, so that carbon can go and attack another carbon which is having a positive charge. So at the end we were able to make a carbon-carbon bond. A new carbon-carbon bond is being made. Now this is a nucleophilic and electrophilic attraction. A carbon attached to the metal is having a negative charge, so it is working as a nucleophile, and this nucleophile is going to attack the carbonyl carbon. And you know what a carbonyl carbon is. Carbonyl carbon is this kind of a group. You can either have a hydrogen or other carbon groups. So if we look into other compounds that may have the carbonyl group, now you can see the carbonyl group in this molecule. However, in the same time we have this alcohol group. Now this hydrogen can be little bit acidic. That acidic hydrogen can interfere with this basic nature. Because this is such a strong base that can even react with water, if the other reactant molecule has any acidic hydrogen, the organometallic compound will show its basic reactivity rather than the nucleophilic reactivity. Now if it is going to react as a nucleophile, it should give us an alcohol. The ideal situation is that this organolithium compound reacting with carbonyl carbon and giving us an alcohol in the place of this carbonyl group. However, if we have this additional alcohol group because of this additional hydrogen which is acidic, instead of showing the nucleophilic reactivity, it will go into an acid-base type reactivity. Now this is going to work as an base, and this hydrogen is going to work as an acid. So what we are going to end up with is an alkane plus this ion. Now the desired product is not an alkane. While it can be kind of used to generate alkane, it is not the ideal way to generate alkane. So this is a limitation. So if you inspect other compounds that you know of, alcohols, they have this acidic hydrogen, and amides, we are going to look into them later. Amides have the general structure of you have carbonyl group, you have the carbon chain, and you have nitrogen H2. and these hydrogens can be replaced by the carbon group. So this is an amide. Again, you can see the carbonyl group. What happens is, if you have a carbonyl group, instead of attacking this carbonyl group, this organometallic compound will try to steal hydrogen from here. And then carboxylic acids. Carboxylic acids are going to be double bond OH. So what's going to happen is, this organolithium compound, instead of attacking this carbon, it will work with this hydrogen, resulting in alkane instead of alcohol. Now that is a limitation in this organolithium and organomagnesium compound. The reason is they are very strong bases, so that they can easily react with any even a slightly acidic hydrogen.